Hello class, in this video we'll be looking at energy changes that occurs in a chemical reaction and then introduce you to the idea of enthalpy. I'll begin this video by talking about chemical energy. Every substance carries chemical energy stored inside of chemical bonds. This energy results from the attraction between electrons and protons, the repulsion between nuclei, the repulsions between electrons, the movement of electrons, and finally the vibrations and rotations that occur around a chemical bond. Because the composition and types of bonds found in each substance will vary, the total amount of chemical energy stored in the chemical bonds will also be different. This is reflected here in this table where you can see different amounts of energies associated with different types of bonds. In a chemical reaction, we know that atoms rearrange themselves by breaking bonds and forming new bonds. Breaking existing bonds in the reactants requires energy from the surroundings, whereas energy is released back into the surroundings when new bonds are formed. You can see this process with the following chemical reaction between hydrogen and oxygen gas. In this reaction, energy from the surroundings is needed to break the bonds present in hydrogen and oxygen gas. As a result, this enables the atoms to rearrange themselves in a particular orientation to form new products. In this process, new bonds are formed which results in the formation of water. Because the number and types of chemical bonds has changed in this chemical reaction, all chemical reactions will undergo a change in energy. This is due to the differences in the amount of stored chemical energy between the reactants and products. You can have chemical reactions where the energy content in the products is greater than the energy content in the reactants. Because more chemical energy is found in the products, the reactants will need to absorb energy from the surroundings in order for this reaction to occur. In other chemical reactions, the chemical energy stored in the products is less than the stored energy in the reactants. Since energy is conserved, the excess stored energy in the bonds of the reactants is released into the surroundings as heat energy. As a result, we can classify chemical reactions on the basis of the direction of energy transfer. We can classify chemical reactions that release heat to the surrounding environment as exothermic reactions. Energy is released because the energy content of the reactants is greater than the energy content of the products. On the other hand, endothermic reactions are reactions that absorb heat from the surrounding. Because the energy of the reactants is lower than the products, it will need to absorb energy from the environment. Now that you have developed an understanding of chemical energy and that energy changes accompanies all chemical reactions, I'm now going to introduce you to the concept of enthalpy. When we're talking about the chemical energy of the system, we could also refer to this as the heat content or enthalpy. All these words can be used interchangeably, but enthalpy is the most common. Enthalpy is the chemical energy or the heat content of a substance at a given pressure and is represented by the letter H. We use the letter H because we are interested in the direction of heat transfer in a chemical reaction. Since we know that all chemical reactions involve a change in enthalpy or a change in energy, this can be represented mathematically by the following equation. Delta H, or the change in enthalpy, equals to the enthalpy of the products subtracted with the enthalpy of the reactants. In an exothermic reaction, we said that energy is released to the surroundings. We can explain this by saying that the enthalpy of the reactants is greater than the enthalpy of the products as shown over here. In contrast, energy is absorbed in an endothermic reaction. By absorbing energy from the external environment, the enthalpy of the products is greater than the enthalpy of the reactants. By finding the change in enthalpy in an exothermic reaction, you'll find that this will always produce a negative value because you're subtracting a smaller value with a larger value. On the other hand, when you're finding the change in enthalpy for an endothermic reaction, this will always give you a positive value. I would like to add that if your chemical equation also shows the changes in enthalpy, this is now regarded as a thermal-chemical equation. Changes in enthalpy are not limited to chemical reactions. The energy content also changes in physical reactions when a substance also changes from one state to another. For example, in order for ice to melt to water, it would need to absorb the energy from the environment, and because it's absorbing energy, this process can be regarded as endothermic. We know that this is an endothermic process because the enthalpy value is positive. Similarly, this is also demonstrated here on the energy diagram as well. Although the usual name for delta H is the change in enthalpy, we use different names for delta H depending on the type of chemical reaction. For instance, it might be referred to as the heat of formation when you have basic elements forming a compound, but you could also see the other types of enthalpy changes as shown in this table. For now, I just want you to be aware of the different types of enthalpy changes, and we'll go through this in more detail in future videos and examples. The next thing that I would like to talk about are the units we use to measure the change in enthalpy. Since enthalpy measures the thermal energy absorbed or released in a chemical reaction, the units for enthalpy is generally in joules. However, because the heat content absorbed or released by a chemical reaction will vary depending on the amount of starting material we've got, it's usually common for the units of enthalpy to be expressed in kilojoules per mole or kilojoules per gram. These two common units for enthalpy can be converted from one another as shown in this flowchart, but we will look at these calculations at another time. To conclude this video, we will look at an example on how to calculate the change in enthalpy from an energy diagram. In this example, it wants us to classify the chemical reaction and to calculate delta H. The change in enthalpy can be found by subtracting the enthalpy of the products with the enthalpy of the reactants, so I'm going to use a calculator and press 2648 minus 3466. This will give us an answer of negative 818 kilojoules per mole. Based on this value, I can confirm that this is going to be an exothermic reaction because the change in enthalpy is a negative value. Now that we've covered the content, I would now like you to check for your understanding by answering a few questions. In the first question, select the appropriate statement about an endothermic reaction. Endothermic reactions absorb energy from the surroundings, hence C is going to be the correct answer. In the second question, it wants you to comment on the value of the enthalpy change for a combustion reaction. Using our prior knowledge of combustion reactions, we know that this chemical reaction releases heat. As a result, the change in enthalpy will take on a negative value. For the last question, classify the chemical reaction and calculate the change in enthalpy given the enthalpies of the reactants and products. To start off this question, find the difference in the enthalpies of the products and reactants. This will give me an answer of positive 375 kilojoules per mole, and because it takes on a positive value, this means that the overall reaction is endothermic. By now, you should be able to meet all the success criteria in this video. Thank you for watching, and I'll see you guys again in the next one. Bye.